Hi, welcome back. This is Ken, and we're on lesson 3 of our course in mechanics, and this is about motion in 2 or 3 dimensions. In this video, we're going to extend our learnings on the previous lesson on motion in 1 dimension into 2 or 3 dimensions. This is again a PowerPoint lecture presentation created for the book University Physics, 13th edition by Young and Friedman. And this will be our goals for this lesson. First, we're going to use vectors to represent the position, velocity, and acceleration of a body. Second, we're going to describe the curved path of a projectile. And third, we're going to investigate circular motion. We begin our study with the position, velocity, and acceleration vectors. So what we have here again are our equations of motion with constant acceleration. And we had versions for the horizontal motion, and we also have versions for the vertical motion. And on our previous lessons, we've used these 4 equations for several examples, like say for example, moving on a straight road with constant acceleration or on freely falling bodies. And these are just again one-dimensional motions. However, if we try to explain the motion of a paper plane, and you will observe that paper planes do not move only in straight lines. So in this case, we need to extend our lesson on 2 or 3 dimensions. Because again, your paper planes does not move, or your paper planes do not move only on straight paths. So how do you describe the motion of the paper plane? If you try to fly one, okay, you'll observe that paper planes do not move on straight path, or it doesn't move on a straight line once you throw the paper plane horizontally. Or if you're going to throw a paper plane vertically upwards, you'll observe that the paper plane will not move upwards and then just go downwards. You'll observe that paper planes will travel or move in paths, like say for example, like what we have here on the figure. And these are mostly curved paths. And curved paths are paths which can be described in 2 or 3 dimensions, and it is not enough to describe this path only using your one-dimensional motion. So this is what we are going to talk about in this lesson, extending our knowledge on motion in 1 dimension into 2 or 3 dimensions. So to start with, let us talk first about the position vector. So if you remembered before, we started lesson 2 with the distance and displacement. And your distance and displacement both talks about your position. This time you're going to talk about the position vector. The position vector is a vector that goes from the origin of the coordinate system to the point P. Consider, for example, in this figure here, okay, we have here your point P here. Again, this is your XYZ plane, and at the center here you have your origin, and you have some point P here. Okay. Now your position vector is the vector that goes from this point here at the origin towards this point here at point P, which here, in this case here, we labeled your position vector as your vector R. The position vector from the origin to point P has the following components. It has a component along the X, okay, as it go, you have this component here, and it also has a component along the Y, and it also has a component along the Z-axis. So your position vector R is a vector in the 3-dimensional space. And using the unit vector notation that we have described on lesson 1, your position vector R can be described as the vector R is equal to xi hat plus yj hat plus z k hat. Now let us talk about the position and displacement. So again, the position of an object is described by its position vector. You have your vector R that's equal to your xi hat plus yj hat plus z k hat. And if we consider for this example in the figure here, we have 2 points. You have point A here and then point B here. And your point A is described by the position vector Ri, and your point B is described by the position vector Rf. So these points here are let's just say positions of a particle at a certain time, at initial time ti, and then at final time tf. Now, of course, your position vectors are described by or has an x and y component, as you can see. So in here, your ri, it has an initial component x I hat plus you have your y initial j hat. The same is true for your rf. Here your rf, your vector rf is described by xf I hat plus yf j hat. Okay, so these are the position vectors describing your position A and your position B. Now, just like we have talked about displacement on our previous discussion, we also have a version of displacement here in the 2 or 3 dimensions. So again, the displacement of the object is just defined as the change in the position. That is, if you're going to look at in this figure here, your displacement is just your change in position from position A to position B. Or that is, you have your delta R is equal to R2 minus R1. Or for this case here, we have your delta R is equal to your RF minus your RI. And as you can observe, okay, so for the figure, we have your delta R that is equal to your RF, okay, minus your RI. And we have here your RFs, and you have here your RIs. So your delta R is just you have your XF I hat plus your YF J hat, okay, and this is minus your XI I hat plus your YI J hat, okay. So this is your displacement for your figure here. And later you can just combine your x and then your y's. So you have your xf minus your xi. Oh, let me just write. So here you have you can combine the x. So you have your xf minus your xi I hat plus your yf minus your yi j hat. Okay, so this is just if you try to look at this is just actually your x component subtracted, okay, and your y component subtracted, which is quite interesting because as you can see, your motion in 2 dimensions is just actually a combination of your motions in the horizontal motion and on the vertical motion. Let's extend this one to the average velocity. So again, the average velocity between two points is the displacement divided by the time interval between the 2 points. And it has the same direction as the displacement. So before, if you can remember, you can still remember your average velocity along the x, okay? P average along the x is just your delta x over your delta t, and then your average velocity along the y is just your delta y over your delta t. Here, your average velocity vector is just the change in your displacement r, described by your position vectors r2 and r1. So your average velocity is just your r2 minus r1 divided by t2 minus your t1, or you have your delta r divided by your delta t. So the average velocity between points is independent of the path taken, just like how independent of the path taken is your displacement. Again, this is because it is this it is dependent on the displacement, also which is also independent of the path. Now, the instantaneous velocity is the instantaneous rate of change of position vector with respect to time. So we're talking about here again the velocity at an instant. So the components of the instantaneous velocity are your Vx is equal to dx over dt, your Vy is equal to dy over dt, and then your Vz is your dz over dt. So these are just your individual components along the x, y, and z axis. So this is just the same concept with your instantaneous velocity we have described in your motion in one direction. We just extend this one to two or three dimensions. And the instantaneous velocity of a particle is always tangent to the path, just like what we have described previously on our previous discussions. And it can also be seen here on the figure. You have your instantaneous velocity vector b, which is always tangent to the path. So if this is here your path, the blue dashed line, okay, if your path here is this blue dashed line, okay, so any point around here and then we draw some tangent line, that is your instantaneous velocity for that specific point or for that specific instant. If that is the case, the instantaneous velocity is the limit of the average velocity as delta d approaches to 0. So this is just the same definition with what we have on our one-dimension problem. So here we have your velocity vector v is equal to the limit of delta r over delta t as delta t approaches to 0, or that is just equivalent to your time derivative of your delta r over your delta t. So this is just the same with your along your x. So your x instantaneous velocity, you have your dx over dt, and your y instantaneous velocity vy, you have your dy over dt. You have your time derivatives. So in here, you have your velocity v is equal to your dr over dt. Now again, your position vector r, it has the following components. It has xi hat plus your yj hat plus your z k hat. And if you're going to take the time derivative of this function here, we just have your dx over dt I hat plus dy over dt j hat plus dz over dt k hat. But again, you have here your dx over dt. This is your vx component. This is your vx, and then your dy over dt. That is your vy instantaneous velocity. So that means here, this one here is your vx. This is your vy, and then here that is your vz. So your velocity vector v is now you have your vx I hat plus vyj hat plus vz k hat. So we now have our position vector, and we also have now your velocity vector. Now let us now talk about the acceleration vector. We have here your average acceleration. If a particle moves from point 1 to point 2 with velocity v1 and v2, the average acceleration of your particle is given by your vector A average is equal to your v2 minus v1 over p2 minus p1, or that is just your delta v over your delta t. Note that the acceleration is a vector quantity in the same direction as your velocity vector. So wherever your velocity vector moves, your acceleration vector has the same direction with your velocity vector. Now the instantaneous acceleration, on the other hand, which is the instantaneous rate of change of the velocity with respect to time. It's just the same instantaneous velocity that we have talked about on your motion in one dimension. So here, your instantaneous acceleration, which is represented by vector A, is equal to the limit of delta v over delta t as delta t approaches to 0. And this is just equivalent to saying the time derivative of dv over dt. If you can remember, so previously we have your instantaneous acceleration a, or your acceleration a along the x. You have this is just your dvx over your dt, and then along the y you have your dvy over dt. Okay, so now since we have your velocity vector v, you have your vx I hat plus vy j hat plus pz k hat, and if we take the time derivative of this function, if we take the time derivative of this function, you have your d over dt. Okay, so we have this expression here. So your instantaneous acceleration vector a is equal to your dv over dt, which is equal to your dvx over dt I hat plus dvy over dt j hat plus dvz over dt k hat. Now since this is just your acceleration along the x, your acceleration on the y, and we have here the acceleration along the z, we can rewrite this one so that your instantaneous acceleration is just your vector a is equal to ax I hat plus ay j hat plus az k hat. So we have here again your four equations of motion for constant acceleration. We have for your horizontal motion and for your vertical motion. And for a particle moving on the xy plane, we have described your position vector earlier. We have your vector r is equal to your x I hat plus y j hat. And your velocity vector, you have your vector v is equal to vx I hat plus vy j hat. And then your acceleration vector a, your vector a is equal to your ax I hat plus your ay j hat. And by analyzing here, your horizontal motion is just actually your x component for your velocity vector, and then your vy here is just your y component for your velocity vector. So if you try to see, we can actually combine these two equations here so that we can only have one equation or one vector equation for this motion here. So with this equation here, so with your third equation and with your fourth equation. Now, let us consider, for example, your vector 1, okay, or your equation 1. So here we have your vx is equal to your v naught x plus axt, and then we have your vy is equal to v naught y plus ayt. Okay. Now let us look at the velocity vector. Your velocity vector v is just your vx I hat plus your vy j hat. Okay. Now we have here a term for your vx and we have here a term for your vy, and then let us use these two equations here. In this equation here, we substitute these two equations to our velocity vector equation. So if we do that, you have your vector v is equal to v naught x plus axt. So this is just plus, we have still here the I hat, and this is plus v naught y plus ayt, and then we have here your j hat. We can combine like terms, you combine the velocities, and then we combine your acceleration. So your equation will become your v naught x I hat plus your v naught y j hat plus you have your ax I hat plus your ay j hat times t. And as you can see, your v naught x I hat plus your v naught y j hat is just equal to your velocity vector v naught. So that is your v is equal to your v naught vector plus here your ax I hat plus your ay j hat is just your acceleration vector a. So you have your vector a and then times t. So we have combined your two equations to write it in a single, into a single vector equation. And you can also do this for your equation number 2, 3, and 4. Just, you just use these definitions here.